Okay, so now we will move to our technical presentation. Our speaker today is Gabriel Jönsson. Gabriel is an ASIC verification engineer at Axis Communication Sweden. He was graduated from Lund University Faculty of Engineering with a master in Systems on a Chip. Shortly after, he started working for Axis Communications as a verification engineer. Since then, he has become the Scrum Master for one of the verification teams, and his paper was awarded a third best paper at the DVCon US 2020. Gabriel will speak about the SystemVerilog framework for efficient randomization of images. And again, during the presentations, feel free to ask questions on Zoom chat. Gabriel, the stage is yours.
Thanks a lot. I'll ask the mandatory question first. Can you hear me?
Yes, we hear you.
Classic video conference call. Thanks for the introduction. So again, my name is Gabriel Jönsson, here presenting from southern Sweden. It's a town called Lund, where Axis has its headquarters. We're mainly located here in Sweden. So yeah, what I will present today is a paper we presented at, or I presented at DVCon 2020 in March. So that was just briefly before the Corona crisis started, and so we were lucky to be able to attend. And I'll kick things off. Let's see if I can share this correctly. Can everyone see that? Good. Yeah. So actually, the full title, even being partially introduced a part of it, SystemVerilog framework for efficient randomization of images with complex interpixel dependencies. So for you who don't know, you have to have a complicated long title for your papers at DVCon, so people will attend and think it's an interesting title. It's very important, and like kudos to Lars Wikland with writing this title. So just a brief introduction of what I'm going to talk about. So just a brief introduction of what we have done. I will continue with some implementation details and some examples, and finish with some results and conclusions. I think you all recognize a classic technical presentation. So to kick off with, as was said already, I work for Axis Communications, and Axis main products are network cameras. So for these network cameras, we develop our own system on chip in-house, here called the ArtPic, which you can see on the left. And the ArtPic does most of the data transformation in our cameras. So from raw sensor data from the outside to pixels presented on the screen to the user. So the internals of the ArtPic mostly consists of like data handling, so handling pixel inputs and outputs, different modules, and that's where most of our verification effort is based. So basically randomizing pixels arranged in frames, say for example here in RGB format. And we in general just randomize these pixels freely, able to close coverage like that. But we realized after time that we had a cumulative number of test benches where we had to create some kind of dependency between pixels in the whole frame to be able to close coverage. So say, for example, that you have some module which calculates the difference between two pixels. It's quite natural that you would want to add some coverage, which we hit if we see the absolute maximum difference between two pixels. But since the number of bits in the pixels can be quite large, it would be quite unlikely that you would hit this just by randomizing the pixels freely. So just to reiterate, so we differentiate between designs where we can close coverage just by randomizing our data freely, and designs where we have some kind of function of neighboring pixels, which we need to close the coverage. So just some examples of how this can look like. Just so the chest pattern we have seen now, but other examples like here in the middle is this kind of frequency pattern, which is useful for closing some compression algorithms which operate in the frequency domain. To the right, we have a more a sharp edge through the image, useful for closing algorithms which work with edge detection. And for you who have written a lot of constraints here, I imagine there are a couple, you might realize that the chess pattern, that's a fine level of granularity to write constraints on pixel by pixel level, constraining pixel against each other. But as soon as you get to this frequency pattern in the middle or the sharp edge on the right, it's quite complicated and hard to write these constraints. And then also take into consideration that usually these blocks or these modules don't operate on the whole frame at the same time. They operate on some blocks of pixels. So to not waste a lot of frames and pixels on redundant data, we would probably want to create a lot of these patterns in one image. And you can imagine that if you have written these constraints once, you wouldn't really want to just copy this code somewhere else or try to modify it. So there could also be different flavors of these patterns, of this problem, like maybe you have 2 sharp edges through your pattern instead. You really don't want to copy these constraints every time. So with the realization that we had this problem, we said that we didn't really want to randomize patterns this way. What we wanted to randomize instead was these kind of high-level features instead. So what is a sharp edge really? It's 2 endpoints on the pattern and 2 colors. That's it. That's everything we need. So what we realized that we wanted to create a kind of framework which contains some kind of stencil. Here, stencil being the tool which we can apply on an image to create a pattern. So we want to create a framework for this, which could be reusable. And not just reusable, we realized there were a couple of other high-level goals. So we wanted this framework to operate on these high-level features. So randomizing our features on a raised abstraction level, not on a pixel by pixel level. And reusable in the sense that we would want to put our solutions, our stencils in a library, which we could import over and over again, and not having to reproduce every time. And maintainable in that we wanted to, of course, maximize our code reuse to not accumulate a technical debt over time. That actually brings us to the actual implementation, how we have structured our framework. And the base framework is basically just these 3 classes. We have a base stencil, which adds all the common functionality of what the stencil needs. We add the single stencil, which is used for creating one type of pattern, say just a chess pattern or just a sharp edge pattern. And then we have the composite stencil, which I will talk more about, but the intent is basically to be able to create the constraint hell we looked at before. So from one single stencil, you could create that large pattern. And I know that even though this is a bit of a simplified image compared to what's in our code and what's depicted in our paper, and just to say that also you can find the paper on the DivCon homepage. You can download it yourself. Interesting read, kind of recommend it. But in any case, there's a lot of details in this image, so I'll step through it a bit more in detail. So the base class, the base stencil is parameterized on 2 parameters. The first one being the number of dimensions we want to apply the stencil on. And what do I mean with dimensions here is that if you have this stencil and you have applied it on a 2-dimensional image, which are our most common use case, say that it creates a chess pattern. But they realize that our data structure is not a 2-dimensional frame anymore, it's some kind of 3-dimensional cube. That should not really matter for our framework. So we have built in this functionality to make our framework agnostic to how many dimensions it is. But we need this parameter which ripples down the class hierarchy. The second parameter is the type of the pixel. So again, the framework shouldn't really care about the specific type of the pixel, but for reasons we'll see, we need this parameter. And the pixel type can be really anything. It can be an integer, it can be a packed struct, it can be a class. But to get this work, we need this parameter. The base class contains one abstract function, abstract since we want the concrete implementations to define this themselves. And this function is for applying the stencil on the image. And what applying here means could be multiple things. It could be that it just overwrites the image with the pattern, but it could also take the background image or the image data and blend with it. Say it could take the pixel and just make it darker. Next part being the adapter, which is the argument to the apply function. And the adapter, of course, the name originating from the software design pattern adapter. It's the interface for accessing the background image or the image. And you might ask yourself, why do it like this? Why would you use an adapter? Maybe isn't that making it overly complicated? Well, there's multiple reasons for this, but the main one being that we wanted to decouple our framework from the image representation also. And therefore we're using this adapter. The last part of this image is that I want to explain is this stencil array. So this composite class contains an array of available stencils. So those are the stencils we would want in our image. Just to give an example of this, what that would mean. So from this one stencil to the left-hand side, by adding it to the composite stencil once, we can kind of create the right picture here with multiple sharp edges in them, which is quite neat, and you don't really have to rewrite the constraints over and over again. So from the previous picture, from the structure of how we structured our framework, we hit some hotspots, some things that were a bit tricky to implement, and I would call them features here. So how we decoupled the framework from the data representation, I will present a bit later on. How we support any types of pixels, another one. How we made it really easy to constrain the values inside our patterns, and how we randomize multiple patterns using the composite stencil, I will also talk about, and then the fun challenge of how we support any number of dimensions. The last part here, sadly, you will have to read the paper to get into the details how we implemented that. But it's still quite fun to present it here. So showing how a pattern would look like in 3 dimensions. And of course, to the right-hand here, the 3-dimensional picture. Of course, the pattern will also be part of the inside of this, this sphere. So you don't just see a part of the pattern, right? And sadly, I can show you more than 3 dimensions because it's quite hard to visualize the 4th dimension in slide format. But as I said, please read the paper if you want the details here. Instead, I will go through the details of the rest of the framework instead, how we have implemented that, starting with the adapter. So the actual implementation of the adapter, how that looks like, is that we added an interface class, an adapter class, which all adapters would have to implement. And when it implements it, of course, you were knowledgeable about SystemVerilog. You're forced to define the functions which the interface class contains. Here, the get and set functions. So these used for getting a one value or setting a value to and from the background image. The frame then, frame adapter then is one concrete implementation of what an adapter would look like, containing a handle to the frame here, the frame just being a class which contains the pixels and is parameterized on the pixel type. And then it has to define the get and set functions. Just to get a different view on this, in pseudocode, here again, implementing the adapter and setting the pixel type here, for example, to an int unsigned, passing the frame to the handle in the constructor and having us define the get and set functions. And with this, the single stencil could actually apply itself. We don't really need anything else. And the composite stencil works similarly, very similarly, but it needs a couple of extra steps to actually work. Yeah. So say that we have a composite stencil, just showing here that how it works behind the curtains. The composite stencil, when we create it, contains an array of available stencils. And to this array, we can start adding stencil types. For example, here, the chest stencil. And every time we add a stencil to it, it receives a unique ID, which is important. And this unique ID is just incremented every time we add another stencil. And when we think that we are satisfied with what stencils we want to be part of the composite stencil, we can randomize it. And what we get from the randomization is the bottom here is a representation of some higher level feature which the composite stencil contains. And this being a grid which aligns how the sub-stencils will be aligned inside the composite stencil. And the second part which we received from the randomization is this IDs array. And in the post-randomize function, we will loop over this IDs array, clone the corresponding stencil, randomize it, and put that in our image. And again, since we're just adding one type or a type to the available stencils, when we clone it and randomize it, you see that we get a different version of that stencil. So we will continue doing this by randomizing or cloning and randomizing, cloning, randomizing, cloning, and randomizing. Here again, I'll just put emphasis on that. You see that you get two different versions of this chest pattern, which is neat, since you from just one of these patterns can create a lot of them over the whole image. And you can do a lot of crazy things with this. You can have overlapping patterns, so you can blend two different stencils with each other. You can also add composite stencils as the sub stencils here, making like a recursively smaller composite stencil. But with the time I have at hand here, I'll show you two examples of what you can create with this. So the first one just being a very simple example. If you want to create a pattern where you have a vertical line through your image with two colors on each side, what you need to do to make this work? First of all, I decide here that I want to apply this only on 2 dimensions, making it a lot easier. And we're extending from the single stencil class. We then add the high-level features we want in our pattern, here being the position of the line, where it should go through our pattern, and the 2 colors, left and right color. We add a constraint for keeping the line, which divides the colors inside the pattern. And we define a function called here, calc value. And this calc value function will be called by what I mentioned earlier, the apply function. And the apply function will basically just loop over all the pixels in the image and provide the coordinate here. And depending on coordinates, this function will just return what value the pixel should have, depending on the coordinate. So this everything you need to basically define this kind of structure, and to be able to visualize this, you need an instance of this stencil, and you need an adapter. And then you just can just randomize your stencil, fixing down the size of your image, and apply it with an adapter. And what you get is what you see here on the right-hand side of a pattern with a vertical line through it. So that's very easy, very neat. But to my more complex example of creating a grid of stencils instead, is composite stencil, which contains multiple sub-stencils. it turns out it's actually not that complicated. It's actually quite easy. So what you need is a composite stencil here extending from a class grid, which adds this high-level feature of constraining the high-level features of how the pattern is allowed to be aligned. It adds two substencils in the constructor. So the vertical line stencil we just created and the chest stencil. And then it turns out that the rest of the code for applying the composite stencil to the image is exactly the same as for the single stencil. The only thing we need to do differently is that we add some constraints for the grid. So for the constraining of how the alignment of the different patterns should look like. And that's it. And this is to be expected, by the way, also since they're both the composite and the single class is extending from the same base class. So we have created a couple of examples of what we have seen that we needed, and we have already started building our own library of these kind of stencils called here AXTencilLib. So the vertical line stencil we just created earlier became the more general sharp edge stencil. We also saw that in a library it was beneficial to break out but the binding of the dimension parameter, since we are most often using two-dimensional images. We also created this tiling stencil, which is used for patterns which are repeating over and over. And that could be like the tiles of a chess pattern, which turned out to be a recurring problem. So we broke that out. And that's the benefit of structuring our code like this, to be able to reuse different kinds of functionality without having to repeat the code. And one of those functionalities is something that we put into our base class here, or the top class in this package called single value. And I know it's not obvious from the class name what that class actually does, but it adds some key functionality to be able to compare stencils and clone stencils, and also to be able to randomize our pixel values or possible pixel values as part of the stencil. So just to expand on that. So given that we have a stencil, we don't know what the pixel type will be until we instantiate it, since it's parameterized on the pixel type. So we don't know how we would clone or compare pixels. So to solve this, we add another class which we parameterize our stencils with, here being the value wrapper, which you can see on the left. And again, this is an interface class. And the values wrapper is intended to wrap the randomized possible values that should go into the pattern. And that class extends from UVM object. So when our stencil instantiates the values wrapper, it can for sure know that the values wrapper has all the functionality that is defined by UVM object, so as comparing and cloning. And the only thing that the values wrapper interface class requires is that the concrete implementation defines the get and get size functions. So get is getting one of the possible values, and the get size is getting the number of possible values. One concrete implementation again would be that we would want integral values as our pixels. So again, we need to implement the values wrapper to create our integral values wrapper, forcing us to define the get and get size functions. And then it's just containing the values array with possible values, which we can randomize. But we encounter another problem here, and that is, how do you actually constrain your values? If you say that you only want two different values in your pattern, say your chess pattern, for example, you only want black and white values. You could, of course, put the constraints directly here in the concrete integral values class, But that would quickly clutter the class, just building up more and more constraints. And also it's fully possible that if you have written those constraints once, you maybe want to reuse those in multiple contexts. Say that you have another value wrapper, which is using packed structs instead. You might want to use the same constraints there. So what we decided to do is using a method which was presented at DVCon in 2016 by Nelson, so kudos to him, and that is using the decorator design pattern. So the decorator design pattern makes it possible for us to add constraints dynamically during runtime. And the way we do this is we introduce another class for this called the base decorator, which extends our concrete integral values wrapper. The base decorator adds a handle to that values wrapper, which is passed in the constructor, and then it adds some constraints which keeps the handle and its own values in sync. And then you can just subclass the base decorator and add the constraints there. And the intent there is to add one specific type constraint, not a whole bunch, but one type, like here being the max decorator, which could truncate our pixels to some maximum values. And it might not be obvious why this is beneficial, why this would be easier. So I'll show you an example, and it's actually quite neat. So say again that we have created our integral values, and say that we want to constrain these values. Say that we want only red, green, and blue values. So we add our decorator by constructing it and passing the handle to the values and reassigning the values. And say now that we also want to only have few values in our pattern. We can just, again, chain this handle together, and we want only even values. We can, again, choose chain the handle. We want to truncate our values to some maximum. Chain the handle, and in the end, it's just a simple assignment. So if you have this decorator all within some library, which you can reuse, it's quite easy to just add these constraints when you need them. Sorry, just this taste there. So this is basically the whole framework. And before I finish presenting the framework, there's one last thing I would like to show you also. And that is some measurables. So we have measured the randomization time here of randomizing a square image, which should contain a chess pattern. And we have compared two approaches to randomizing this image. The first one being just, as I mentioned in introduction, by constraining the pixels against each other. So if one pixel is white, then the next one should be black, and then just constraining them all together. What we realized though is when we started randomizing larger and larger images with this, that the constraint solver just crashed when we reached a square image of 128 times 128 pixels. And that's of course because once we reach that point, we have created this kind of massive equation system, which is a huge burden from the constraint solver. And important to note here also is that the scale on the y-axis is logarithmic, which kind of puts emphasis on how much time this actually takes. But the second approach was using our framework instead. So here being the blue line. And what we saw is that because we're not randomizing each pixel and constraining them against each other, we're only randomizing these kind of high-level features. In the chess stencil case, for example, it would be how large is a tile. And that scaled them much better. And that's because we're randomizing these high-level features and then applying them in sequential code. And we were able to create larger and larger images with this, larger than what you can see here in the graph of 4K times 4K image. And that is the whole presentation of how our framework works. We're quite satisfied with results. We have started using it and rolled that out. And what we have seen in this presentation is how we can create multiple flavors of one stencil and creating multiple patterns of that. We have seen how we can easily reuse our solutions by putting them in a library and just importing them over and over again. We have seen that it's applicable. Our framework is applicable for most or all use cases we could come up with, at least, even if we would find a 10-dimensional data structure in the future, our framework would still work. And we have also seen that the performance is a lot better in our case, and that makes it better than any ad hoc solution we could come up with anyway. And that's all I have prepared currently. Thanks a lot for listening. I hope you enjoyed it. And I think next up is some questions, if you have any.
Thank you, Gabriel. Elichai, are you here? You want to ask a question?
Yes. Hi.
Hi.
Hi, thank you for your presentation. Actually, I have two questions. One is a bit out of topic. At first, when Rachel presented you, she said you are a Scrum Master for some project.
Yeah.
If time permits, I will be happy to hear how is the Scrum and Agile methodology is working in verification development. But this is if we have time.
Yeah, of course.
Or if you can point me to some material in this would be great. Second question is related to the presentation. I didn't quite understand what, let's say in the two colors image, the simplest one.
Yeah,
what is done in what is randomized and what is done in post randomization? Because if I would simplify how to randomize a two-color image, so I said, okay, randomize two colors. This is the simple constraint, and then randomize the point on the x-axis at which the color switch, and then in post randomize fill all the pixels. So I want, yes, the calc value. When each part of the class is called in randomization, post randomization, pre randomization. Yes.
So just for this simple single class, this is basically what is done to apply the image. So applying it with the adapter. For the single stencil, it's nothing that is really done in the post randomized function. Really, so it's only randomizing these high-level features, which in the simple case is just the line position and the two colors, right? And then when you later on apply it with the adapter, that's when you start looping over the pixels and apply the...
So, okay, I understand. So adapter is like post randomization. It's logically it's the same.
You could see it like that, but this is a lot more general again, since you could use the adapter in multiple contexts. While if you just hard code a post randomized function here, you would have to recreate that post randomized function for every type of pattern you want to create, right?
Yes, I agree. It's okay. Now, okay, this is a good idea. Okay, great.
I hope that answers it.
Yes, I was one. It's clear.
And for your Scrum question, I get what you're asking. It's not completely obvious how you use Scrum in a verification environment or in a verification team, right? Or ASIC projects, which where your cycles, your development cycles are a lot longer. I don't have any specific material to point to. It's been a lot of iterations in our ends ourselves, but feel free to contact me if you want to talk about it more.
Yes, I will. Thank you.
Perfect.
And we have also a question from Elhanan.
Hi. Okay, I promise it's nothing to do with formal. Okay, you spoke about, the talk was about stimulus. I'm wondering, how do you verify that the result is correct? You have some golden MATLAB or C reference golden model that you run the same pattern through?
Yes, so this is just the stimulus generation. So it's from our side completely orthogonal to the checking. So this is just how we randomize data, right?
Okay.
But yes, we often use reference models, and it would have to be fed the corresponding data, right?
Okay, so that was a loaded question. The second part of the question is, if you're already having to go outside simulation, outside Verilog or VHL simulation to check that your results are correct, do you find that generating the whole framework here in UVM is more efficient than if you're doing a similar functionality of stimulus generation in C or MATLAB or any other tool language that could generate patterns?
I think that one of the huge benefits of SystemVerilog is its rich use of constraints, basically. That's not always obvious how you would do it in other languages, and I think it's a huge benefit to do it in SystemVerilog.
You mean exploiting the constraint solver within SystemVerilog?
Yes. Yes. And I think the formal question is kind of orthogonal again.
No formal.
No, we have seen that that's kind of a completely different topic, that you can use the framework so you can extract stimuli using formal, like how do I hit this specific point, feed that back to our framework, generate patterns with the result from formal, and create the patterns that way, which has also been a benefit.
Okay, thank you.